Hello and welcome to yet another lecture on basic electrical engineering paper code ESEE 101. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is Buck Boost Converter. It's an objective. After end of this topic, students will be able to understand the working of buck boost converter. So buck boost converter, a DC to DC buck boost converter circuit that combines the operation of step up, or in other words, you can say the boost converter and the step down or the buck converter. From the name, it is clear that it is a combination of stepping up, that is the boost, and step down, that is the buck converter. The output DC voltage can be either higher than or equal to or lower than the DC input voltage. It is also possible to reverse the polarity of DC output voltage. This is the basic circuit diagram of buck boost converter. So, we are using a switch. We are using a switch that is, it can be of any type, solid state device that can be used for switching like power transmitter, thyristor, GTO or IGBT. This is the general basic circuit diagram of buck boost converter. So now I am coming to the operation of buck boost converter when the switch is closed. This is the operation of buck boost converter when the switch is closed. When the switch is closed, that means the diode is on. When the switch is closed, that make the diode D is reverse bias. That make the diode D in reverse biased means there is no current, that is the current through the diode is now zero. The current through the diode is zero. Reverse bias means the diode will act as an open circuit. So it is clear from the figure that the diode is act as an open circuit and there is no current through the diode. This is the input voltage and the current is routed through that particular part. Current is routed through that particular path. So, it is now clear that the voltage across the inductor, that is V suffix L, is now equal to the input voltage V suffix I. As a result, when the current is routed through that particular path, when the switch is on of a buck boost converter, it will allow the current to flow through that particular path. which in turns build a voltage across the inductor, and the voltage across the inductor, that is V suffix L, will be equal to the input voltage V suffix I, and also the current, that is I suffix L, through the inductor, that is increasing linearly with time. The current through the inductor, that will increasing linearly with time. Now, let us take another operation of buck boost converter. When the switch is off, when the switch is off, it is clear that the source, that is the VI, that is disconnected. When the switch is off, the source, that is VI, is disconnected, but the current through the inductor, that the previous current that is going on through the inductor, means the IL, can't change instantaneously. So the current through the inductor cannot change instantaneously. But when the switch is opened, the source becomes disconnected. So now it will make the diode in the forward bias. And we know that when a diode is in forward bias, it means the diode is act as a closed switch. It is clearly seen in this figure that diode is acting as a closed switch. So now the output voltage, that is the voltage across that resistance, that is the output voltage, that is V suffix O or VO, will be same as the inductor voltage VL. It is clear because there is no source in this. When the switch is open, there is no source is acting. So as a result, it will make the diode forward bias. I mean, diode is now in operating condition, and the output voltage, it is clear that output voltage is now equal to the voltage across the inductor. It is clear when the switch is off. So if I now see the current waveform, it is the time period T1 when the switch is on, and it is again the time period T2 when the switch is off. And the current through the inductor, that is increasing linearly, that we have already told. When the switch is on, the current through the inductor is increasing linearly by following that particular path from its minimum value to maximum value. And again, when the switch is off, it goes on decreasing from its maximum value to minimum value. Means, if I see that it is the current, the same current that is flowing through the diode also when the switch is off. See the nature, same current that is when the switch is off, the same current that is flowing through the diode and also flowing through the capacitor also flowing through the capacitor. It is the same current that is flowing through the diode, same pattern of current that is decaying, that is coming from its maximum to its minimum value, because we have already seen that when the switch is off, the diode is in forward bias or it is working. So means the diode will be follow the same pattern that is followed by the current through the inductor, and also the capacitor is also follow the same pattern. So as a result, the current, that is the input current, it will be follow the pattern linearly, and when the switch is on, but when the switch is off, the input current, there is no input current, because we have already seen that when the switch is off, the source is disconnected. So as a result, there is no input current when the switch is off. Only the input current is there, that is same as the current flowing through the inductor when the switch is on, and it is also going like that. It is follow the pattern of the inductor. Now if I see the voltage across the input voltage or the voltage across the inductor, when the time t1, for the time period t1, it will be Vi equal to VL, that we have already seen. But for the time period t2, when the switch is off, the output voltage became VL. So as a result, we see that the pattern is like that. So this is the voltage and current waveform for the buck boost converter. So when the switch is in on condition, for the time period T1, the input energy W1 is equal to VI II into T1. When the switch is off, for interval T2, the output energy W2 equal to V0 II into T2. So if I, for the lossless converter, both these two powers are same, that is W1 equal to W2. Putting those values of W1 and W2, we get that output voltage VO, or say the suffix O, is equal to input voltage multiplied with T1 by T2. So we all know that T2 is total time period T minus T1. So we can write that, from that equation we can write this particular equation, that is, we can write it in the form that T minus T into T1 by T. So if I take the T common, it will be get 1 minus T1 by T, that is equal to T into 1 minus T. So if I put the value of T0 in this equation, T1 is nothing but T into T, where T stands for the duty cycle, and T2 is T into 1 minus T. So the output voltage became input voltage into D by 1 minus D. So the output voltage that can be controlled by changing the duty cycle D, that is, depending on the value of D, the output voltage can be made greater or say equal or less than the input voltage. This is the general conception of buck boost converter, where the two types of operations can be done. With the duty cycle value that is greater than 0.5, the converter operates in the boost mode, means the output voltage is greater than the input voltage. But for the t less than 0.5, the converter operates as in the buck mode, that is step down purpose. Now from the analysis of buck chopper, we can write that the value of the IL, that is the load current from the graph that we have seen, it is the summation of maximum current plus minimum current divided by 2. So we know that input current, that is equal to D into IL, or we can write, just putting the value of the IL here, we are getting that particular equation, that is I max plus I min by 2 into D. So again, the power input, that is given by Pi equal to Vi II. So we are just putting the value of II in this equation and we will get that input power equation, that is Vi, which is the input power or the average power input, is equal to I max plus I min by 2 into D into Vi. The output power can be given as, that is the P suffix O is equal to V0 square by R. So if I neglecting the power losses of the converter, we can write that these two power are equal. So yes, putting the values of this one for the input power equal to this one for the output power. So we are getting a value of I max plus I min. After doing all the calculation, nothing but replacing the V0 by V0 equal to V1 means we are replacing the V0 value by V1 into D by 1 minus D. We are getting the value of I max plus I min, that is equal to 2dVi divided by R into 1 minus D square. So we switch close for the interval T2. So changing the input current, it is from that equation, that is, if we can write that the change in the input current, that is nothing but Vi by L into T2. So change in the input current can be written as, is the difference between the maximum and the minimum current, that is I max minus I min, that is equal to Vi L Vi by L into T2. So we are putting the values, that is Vi L into Dt. So from that two equations, we are getting the maximum value of I, that is, but with the help of that particular equation, we are getting the maximum value of the I. If I get the maximum value of the I, we will also find the minimum value of the I. So you are already getting the maximum and the minimum value of I, and it is clearly given in these equations. And now the peak-to-peak ripple in the output current, that is given that I peak to peak, that is the ripple value, it is nothing but the difference between the maximum and the minimum value. So peak to peak ripple, that is equal to I max minus I min, and it is clearly the difference between I max and I min, which will give the value, that is this one Vi Td by L, which is known as the peak to peak ripple of the input current. And if you want to obtain the value of minimum inductance that is required That means the I mean that is tends to 0. So this value is now tends to 0. So if I move this value tends to 0, the value of inductor that we will get, that is L equal to RT d by 2 into 1 minus d square. That is the minimum inductance that is required. So we can find it with the help of, when I move the RT value, minimum value of the current, that is this equation is going towards the 0, means when I minimum is 0, from there we are finding the minimum value of L, that is RTD by 2 into 1 minus d square. So now there is a numerical problem that given that a step up DC converter supplies a load of 480 volt from a 230 volt DC supply. Assume the non-conduction period of the switch to be 50 microsecond. Find the on time of the step-up converter. So we know for the step-up converter, the V2, the output voltage, that is V suffix O, that is equal to the input voltage multiplied by T by T2. So the output voltage is given to us, that is 480, input voltage, that is 230. T is nothing but we have to find the on time, that is T1. T means the summation of T1 plus T2, that is summation of on time plus off time. So we can write on time T1 plus off time, that is 50 microsecond, means 50 into 10 to the power minus 6 divided by 50 into 10 to the power minus 6. So from that particular equation, we will find T1 value, that is the on time T1 is equal to 54.35 microsecond, that is the on time of the step up converter. So another problem that we have, that is given that the inductance value of a buck boost chopper is 0.5 millihenry, while the load resistance is 2 ohm. The source voltage is 60 volt DC, while the load voltage is 110 volt DC. If the on period be 2 millisecond, find the chopper frequency, that is the switching frequency, value of Imax and Imin, the average value of the input current, the average value of the diode current, the peak to peak ripple in the input current, the minimum inductance required for the continuous conduction mode. Now first we will start with the chopping frequency calculation. For the bar boost chopper, this is the general information of output voltage that is known to us. So V0 is given 110 volt in this problem, where the Vi is given 60. From that we can easily calculate the duty cycle, that is equal to 0.647. We know duty cycle is T1 by T. So from there, we can easily find the value of T. And because T1, that is the on time, is given in the problem, that is 2 milliseconds, that is 2 into 10 to the power minus 3 seconds. So from the value of from that particular calculation, we have found the value of T, that is 3.09 millisecond. If T is prime, is found, is already We have obtained the D, so we can find the chopping frequency, that is frequency equal to 1 by T. Just putting these values, we find the value of frequency, that is 323, that is 323.63 Hertz. 323.63 Hertz. Now this again, we have to find the maximum value of the current. We know the equation for the maximum value of the current, and all those values are known to us. That is the R, load resistance is 2 ohm, and that is the inductance, that is L is given that it is 0.5 millihenry, that is 0.5 into 10 to the power minus 3. After putting those values, we will find the value of I max, that is 275.85 ampere. Same way, we are finding the minimum value, that is 35.95 ampere. That is I mean. So the third question is the average value of the input current. So average value of the input current is find it by I max plus I mean divided by 2. Just putting those values of I max and I mean that we get the average value of input current, that is I, that is 155.90 ampere. Our fourth problem is the average value of diode current. So average value of the diode current is same as the output current, that is V0 by R, 110 by 2, that is 55 ampere. Now the peak to peak rebel in the input current, that is peak to peak rebel, that is the difference between the maximum and the minimum value of the current. Putting those values, we get the peak to peak rebel value is 239.90 ampere. So another is the minimum inductance required, that we have get the minimum value of the inductance that is required. Just putting the values, that is RTD1 minus D square by 2. So all the values are known to us. So putting those values, we will get the minimum value of the inductance required, that is equal to 0.25 millihenry. So in this way, we can able to solve the problems related with buck boost converters. So another portion is the methods of varying output voltage for DC to DC converter circuits. So we are adapting the two methods are employed for varying the average output voltage for the DC to DC converter circuit. One is known as PWM, or pulse width modulation. So in this method, the width of the pulse, the name suggests that the width of the particular pulse, the width of the particular pulse, this is called the width of the particular pulse, is varied. Means in this method, the width of the pulse of the on time, that is width of the T1, width of the T1 is varied while the overall switching period, that is T, is kept constant. So it is a general configuration when the output voltage waveform for on pulse variation for a DC to DC converter with reduction in T1 to T, that is remain same. Here we are seeing from that particular figure that the T, that is T1 plus 2, that is the total time period remains same, but only variation is in the on time. It is on time is more for the first graph. For the second output, the on time is less, while the off time is more. So varying the width of the T1, that is the varying the width of the T1, that is the on time, we will able to change the width of the pulse, but if the overall time period, that is switching purity constant. Another is the pulse frequency modulation, that is called PFM. In this case, the T1 is kept constant, that is the on time remains the same. The time period is varying, resulting in variation of the frequency of switching. We are now concentrating on the frequency of switching. In order to obtain the frequency of the switching, means we have to make that on time period T1 constant. We have to vary the total time period T, because F is equal to 1 by T. So if I vary the total time period, the variation of the frequency will be obtained for the switching. So this is the output wave from voltage with variable time period. It is clearly seen that for the first and for the second output, the T1 remains same, only the change in the total time period T. For the second output, the value of the total time period is more compared to the value of the time period for the first output. So as a result, there will be change in frequency also be obtained. Now, it is noted that the output voltage is zero, either with PWM or with PFM for off loop, that is T2 equal to 0 of the converter. In PFM method, it is required to reduce the switching frequency to obtain lower output voltage. However, for a very low frequency, this may result in discontinuity of the load. Any reduction in switching frequency may result in more ripple in load current, thereby increasing the losses and heating in the load. At very high frequencies, the electromagnetic components in the DC to DC converter circuit may suffer from higher losses with it. The WM method has the advantage of lower ripple, and hence the filter elements have lower rating. And all these points make the PWM methods more advantage. It will give more advantage to the PWM method. Thank you.